I love mini computers, like this Centurion mini computer that's off to my left here. I also really love Texas Instruments, like this TI-99-4A here. I think this is a really quirky and very fun home computer, but as much as I love it, a mini computer it is not. However, Texas Instruments did make a mini computer. The TI-990 series of machines were quite ubiquitous, but despite my best efforts, I haven't been able to get hands-on with one of those yet. However, the TI-99-4A here has a bit of an ace up its sleeve. The CPU in the center of this, the TMS9900, is actually a large-scale integrated version of the CPU out of the TI-990. So I had this harebrained idea to try and build a homebrew mini computer using the CPU out of a TI-99. And rightfully, a lot of people looked at me and said, why? The TMS9900 CPU is very strange, and it's one of the harder CPUs to try and build a homebrew computer out of. But there's one very, very good reason to use this CPU for our homebrew, and that is that I happen to have a spare white ceramic and gold penned packaged TMS9900 right here. It is one of the most beautiful CPUs I have ever seen, and I desperately want to use it in something. So we're going to use this to build a homebrew mini computer. Now, I said I want to build a homebrew mini computer, but what does that even mean? Well, I think everybody's definition of those two terms is going to vary quite a lot, but in my eyes, a homebrew computer is a computer or a CPU that is hand-built and requires creative effort. And a perfect example, I think, is this UE1. This is my very first ever homebrew computer, and while it is heavily inspired by the Motorola MC14500, Motorola obviously did not build it out of vacuum tubes, so there was an immense amount of creative effort required in bringing this machine up. So what is a mini computer? Well, this one's a little harder to nail down. I think it's because the term mini computer was never really a decided upon thing. So the marketing departments just kind of ran a little wild with it. And I used to be the technical advisor for the marketing department in my previous job. And they'll say anything and everything under the sun to try and get another sale. So I think the term mini computer here is open up to a little bit of interpretation, and my interpretation of it is that it's all about capability when compared to conventional computers of the same era, most notably with respect to multiple users and big storage. So if the year is 1983, this Centurion computer here is absolutely a mini computer because it can support up to 32 simultaneous users, and I currently have it kitted out with almost 100 megabytes, but you could push this thing as far as nearly half a gig in 1983. This is when the IBM PC was just a single user and had 2 floppy drives, and that's it. So yeah, the Centurion here is absolutely a mini computer, and that's my interpretation of the term mini computer. Now, in the previous episode, we built this little card right here. This contains just a single IC. It's the TIM9904. This is a special IC that generates the 4-phase 12-volt clock that is necessary for the TMS9900. We also put a bunch of headers on here with either pull-ups or pull-downs, depending on how we wire wrap those headers, and that's going to become vital once we start working with the actual TMS9900. But before we start cutting out PCBs and plugging them together, let's first take a moment to try and understand what even is this thing, because the TMS9900 is a little different than your usual CPU that you see in a homebrew computer. And this tome of knowledge, the 9900 Family Systems Design book, has been absolutely instrumental in helping me start to wrap my head around this IC. We'll open it up to this page right here. And this is a block diagram of the architecture of the 9900 CPU. Now, as far as the programmer is concerned, there's only 3 registers that are available to them from the CPU itself. There's the program counter, the workspace register, and the status register. Now, there's a few more registers in there, but we don't really need to worry about those. That's a little weird. where are all of our general purpose registers for working with stuff? Where's our A register and our B register where we can store values and do math with them? Well, they're not in the CPU, they're stored in memory. And this is where things get really, really fun. So we'll move over to this page right here. And this is a lovely little diagram showing how our general purpose registers are laid out in memory. Essentially, you have a workspace pointer, and you take that value and you add to it 00, 02, 04, 06, and so on to give the programmer access to 16 16-bit registers. But because the beginning and end of these registers in memory is defined by the value of the workspace pointer, you can change that value and jump to a completely different set of 16 16-bit registers, which means you could have, for example, 2 users, each with their own collection of 16 general purpose registers, and you can jump back and forth between those 2 users. All you have to do is update the workspace pointer, and you can move back and forth really, really rapidly. This is super exciting for multi-user capability, and we're going to lean very heavily on this. But we're going to use this in conjunction with hardware interrupt, which means if we go to this page here, we're actually now looking at the entire memory map for the TMS9900. But if we look at memory address 0000 to 003E, we'll see that this is dedicated to interrupt vectors. Now, what is an interrupt? Well, it's kind of what it says on the tin. The CPU is off running code doing something completely separate, but let's say a peripheral wants to grab the CPU's attention. It'll send an interrupt request that kind of interrupts the CPU from doing whatever it was doing. The CPU will temporarily pause what it was doing and handle the interrupt request coming in from the peripheral. Now what this means is that the CPU can kind of ping pong back and forth between different interrupt requests, preserving the registers of each user that is making these requests and running completely unique code for each individual request. Now, I've been using users hitting data terminals as an example here, but we can also use this to perform something else, like say anything that wants to do DMA, because that is also something that this CPU is capable of. If we push our way over to here, this is an explanation of all of the individual pins on the actual IC itself, and pin 64 is called hold. And this says, when active low, hold indicates to the processor that an external controller, for example a DMA device, desires to utilize the address and data buses to transfer data to or from memory. The processor then places the address and data buses in the high impedance state and responds with a hold acknowledge signal. So what this means is that if a device external to the system, like say a hard drive, wants to deposit some values into memory, it can send a hold signal to the CPU. The CPU relinquishes control of the address bus and the data bus and allows the drive controller to take control of those buses and effectively shovel data into memory at an incredible rate. This is what DMA stands for, direct memory access. This ability to handle DMA, combined with how the interrupts are laid out on the IC here, are going to allow us to achieve our 2 goals of multiple users and big storage. Now, we're not doing any of that today. We're just trying to understand the CPU. And well, I think we're starting to get enough of an overall idea of how the TMS9900 works to potentially plug it into a PCB and see what happens. But that means I've got to make a PCB for it first. So let's fire up the mill and start cutting out stuff. If you missed the previous episode, I go into a lot more detail there about how I'm creating my circuit boards. But one thing that I forgot to mention was how I convert the Gerbers to G-code. For this, I use a program called FlatCam. I'm not sure I would recommend it other than that I don't know any other program that does it as well as this one does. But the barrier for entry in FlatCam is steep. It's not all that intuitive. At any rate, the circuit board appears to be cutting out just fine. No, wait, what? It absolutely does not appear to be cutting just fine. You can clearly see the bit moving across the surface and absolutely nothing is getting cut. What the heck is going on here? It looks like it cut half of it fine. Thankfully, Mrs. Usagi noticed something was funky when she was grabbing something from the garage and let me know. It's like my bit broke or something. Let's stop the cut and check it out. And yeah, wow, look at that. The tip is totally rounded over. I only have like 3 cuts on this bit. It should not have failed this fast, but I was trying a different kind of bit and apparently these are hot garbage. I'll switch it out with a different bit and start the program over again. There's going to be some duplicated movement, but that's all right. It'll go through and clean up anywhere the previous bit failed to do its job. Now, this is the same kind of bit as the one that went bad, but I should be able to get at least 1 or 2 good cuts before this one dies too. After letting the mill drill some holes and do an edge cut, that came out looking fantastic. Now, I know it's a little ridiculous having such fat traces, but hey, that's just my style. And that's what this big honkin' Bridgeport can do reliably. I think it looks excellent. But a blank circuit board just looks cool and that's it. So let's get some components on this thing. There aren't a whole lot of components to go on this one, mostly jumper wires, 1 socket that I had to make out of 2 smaller sockets, and a couple of decoupling caps. And that's it, really. Well, that came out looking absolutely stunning. The white ceramic TMS9900 and all the metal jumpers look brilliant, and we now have our first 2 PCBs for this project. All we need to do now is plug these into each other, but, well, that's not gonna work. We need a backplane to plug these into, and through the magic of hours and hours of work off camera, we have a backplane right here. Now you'll notice that this backplane is quite small. As a matter of fact, it's the exact same size as all of the cards we've been making, which is 150 millimeters by 100 millimeters. This is because all the single-sided PCB that I'm using to machine these out with is that size. So everything about this project is going to be based around 150 millimeters by 100 millimeters. And as such, I've actually designed the backplane to extend and kind of daisy chain using these little connector pieces here. So you plug that into one side and it daisy chains on over to the next backplane. But we haven't cut that second backplane yet because we don't need it. We've got 4 slots that we can use on this one. Now, before I go plugging the CPU and the clock into this, we actually have to do a little bit of wire wrapping on this one first because there are some certain signals that are going to need to be pulled up in order for the CPU to be happy. It should be noted that every signal is going through a 4.7K ohm resistor here, so we're going to use that resistor as a pull up or a pull down depending on how we tie it here. And you can see I've already worked ahead a little bit here. I've got 5 lines tied up to +5 volts. These are the 5 interrupt lines. We're going to have a bunch of different peripherals hitting these in the future, and that's all going to be set up kind of like open collector type stuff, and we'll deal with that then. But for now, that's going to work fine just being tied up. The next signal over is going to be reset, and if we look at the book here, we can see that that is active low. So we want to tie that high. So I'm going to take my little wire wrapping tool here, and we'll set that over there and just get the wire wrap started. And then we will just slot that onto the +5 volt pin right up there. We'll trim the excess off, and then we will give it a spin. And there we go, that signal is now tied high. The next signal is hold acknowledge. That's an output from the CPU, so we don't need to do anything with that. After that is wait. That is also a CPU output. We don't need to do anything with that. The one after that is hold. This is a CPU input, and if we look in the book here, hold is active low, and this is the pin that we're going to use for DMA devices. But for now, we're just going to tie it high so that it's not on all the time. So skip that one, and go to this one. And then we will give it a bit of a spin here. And there we go, that one is now tied high. The next pin is write enable. That is a CPU output, so we don't need to worry about it. After that is memory ready. That is a CPU input. It says ready when active high. Ready indicates that the memory will be ready to read or write during the next clock cycle. And since we don't have any memory hooked up to it right now, I think we're going to want to tie that one high. So that way it thinks that there's always some memory ready and the CPU will actually just kind of free run. And that's it. That's really all that we're gonna have to wire wrap on this thing to hopefully get the CPU up and going. Now all we need to do is plug these into the backplane and try to get some power into it. And I think in order to do that, I'm actually gonna mount all of this to the backing board that has all of our power supplies because that'll make it a lot neater and tidier. Now, I'm confident in my work, but not so confident that I'm willing to risk this rare white ceramic TMS9900. So let's pop it out of the socket right quick and slip in a black plastic package TMS9900 that I have laying around. This is actually an AMI S9900, which I believe is a clone of the TI version built by American Microsystems Incorporated. In order to make all this neat and tidy, let's go ahead and get stuff mounted. I'll line up the backplane with where I want it to live, then I'll pull out the drill and punch some holes in the backing board. Next, I'll use some M3 standoffs and screw them into the wood base. These are actually the same standoffs I used for the UE1, which reminds me, I gotta order some more of these. At any rate, I'll screw the backplane down, and then let's pop in both cards to see how the backplane handles the pressure of trying to force all those double row pins down. And that's not bad, really. I think that'll work nicely. All right, let's work on getting power over to the backplane. I cut up a little power distribution board here, and I'll lay it down right here in the center so it can feed all the different backplanes that will ultimately be mounted. After punching some more holes with the drill, it's time to start soldering the wires that will carry power to this board. This may seem potentially inadequate at first, but remember the density of my circuit boards is hilariously low. When this backing board is fully stacked out, it'll really just be a handful of ICs. It's tedious work, but I got all the power wires to the distribution board routed and connected. And I also routed and connected up the wires from the distribution board to the backplane. Each interconnection that connects two backplanes will have a power input, which means there should be a total of 6 backplanes and 4 power inputs spread across the entire board, which should give pretty nice even distribution. Finally, let's check the power without the cards installed, and yeah, looks like we have good negative 12 volts, plus 5 volts, minus 5 volts, and plus 12 volts. I think we're ready for our first proper test with both cards plugged in. So I've got the multimeter on the ground and plus 5 volts directly on the IC here. I've got the scope on Phi 1, and I have the CPU pulled into reset with this little jumper right here. So let's flip the switch and see what happens. We do have a clean 5 volts. We do not have Phi 1. That's interesting. Aha. Here's my problem. In my infinite wisdom, I didn't extend the clock signals all the way to this front header. So where I'm probing with my scope here is never going to pick up anything at all. Now that seems silly, but I did this for a very specific reason. I designed the backplane to be somewhat customizable. Here's a list of all of the signals on the backplane, and we can see that we have our full 16-bit data bus. We have 5 signals for interrupt request, which can come from anywhere. We have our control signals, which is going to be reset, hold, wait, and so on. Then we have our full 15-bit memory address. Then we have 5 signals that I'm calling spare, and finally we have all of the power bus. Now it's these signals that I'm calling spare that are interesting, because sometimes I need extra signals that are not covered by what's on the rest of the pins to move between 1 or 2 cards. And in this case, I needed the 4 clock signals to move between the clock board here and the CPU board that's going to be sitting in front of it. So I just connected those up. So that means that they're not extended to the, the card edge connectors. But if I'm on the actual chip directly, you can see we've got a clean 5 volts and we have a clean clock coming out. Let's try this again. I've got the yellow trace here hooked directly up to Phi 1 on the CPU card, so we should see the clock come to life there. The remaining 3 traces, the green, blue, and pink one, are going to be memory address 15, 14, and 13. This is a big Indian chip, so the memory address 15 is going to be the least significant bit. But right now I have it in reset with this little red jumper here, so I'm not expecting anything to do anything. Let's turn the power switch on here. And yeah, our clock did come to life, but okay, that's interesting. Our memory address lines, memory address 15 is at 0, but 14 and 13 are at 5 volts. That's very strange. I would have expected them all to be 0, but I don't know, maybe when it's held in reset, it's put at a different value. Let's pull the reset pin here and see what happens. Well, it looks like one of the memory addresses is doing something. Oh, if I slow down enough, check that out. The memory addresses are doing stuff. Let's take a single shot of this. And if we zoom in a little bit here, the The memory addresses are doing the opposite of what I would have expected. We can see that each one is twice as long as the previous, which would imply that AD15 is actually the most significant bit, which would explain why they're so much slower than the actual clock itself. You can see that if I zoom all the way into the clock pulses, we're just barely scooting along there. So let's flip the probes around to AD1, 2, and 3 and see if that makes a little more sense. The CPU is back in reset. Let's kick the power on. And yeah, we still have our super fast clock going on here. The reset levels, again, don't make any sense to me. I think I'm on the right pins here, so let's pull it out of reset. And yeah, we definitely have action going on here. Let's take a single shot. We can see our Phi 1 clock down here on the bottom chugging away at really quick speed. And then we have what is AD1, memory address 1, and we can see that it is cycling at twice the speed as AD2, which again is cycling at twice the speed as AD3. That's kind of what I was expecting to see on 15, 14, 13. I could have sworn this was a big Indian machine, but well, the evidence here is showing that AD1 looks like the least significant bit. As soon as I cut the camera, I figured out what I had done. What's going on here is that there's a miscommunication between past me and present me. The TMS9900 is absolutely a big Indian chip. We can see that in the book here where it lists A0 as the most significant bit and A14 as the least significant bit. But that's backwards to what I'm used to. I really like Little Indian, where A0 would be the least significant bit and A14 would be the most significant bit. So I decided to design everything around Little Indian. So the backplane here, all of the future expansion cards, everything is going to be treating A0 as the least significant bit, which means that a translation has to happen somewhere. And that translation happens on the CPU card itself. So A0 is connected up to A14 on the CPU. This seems like super confusing and backwards, but what it means is that the list of signals that I have here for the backplane is actually correct. When we were on pins AD1, 2, and 3, we were looking at the least significant bits of the memory address. So it's actually working exactly like it should be. It's doing the CPU is running. The CPU is running. It's cycling through memory addresses, looking for instructions to execute. But because it's just a CPU and a clock chip, there's no instructions there to execute. So in the next episode, we're going to try and get 16 bits of ROM onto the backplane here so that when the CPU is cycling through those memory addresses, it can actually grab an instruction out of memory and execute it. Now, granted, we won't have any RAM. That'll be for the episode after next. But once we get ROM and RAM in this thing, we can start doing some really tricky and cool stuff. So this is shaping up just absolutely wonderfully. Our CPU works, our clock works. Aesthetically, I think it looks stunning, and I'm super happy with it. I hope you guys are as excited about this project as I am, and I want to thank you all so much for watching, and I hope to see you in the next one.